Hi everyone, welcome back. We just started chapter 4 and we have already introduced three new types of convergence. These notions, they are dealing with convergence of sequences of bounded linear transformations between, well, normed linear spaces. There's the uniform convergence on the very top, then the strong convergence, and then the weak convergence. That's a tower. Uniform implies strong, implies weak. In general, you can't reverse the arrow directions there. I gave examples why that's the case. Now, if you think back to the last section of the previous chapter 3, there we talked about weak convergence and weak star convergence. And one of the important properties was that if you have a sequence that converges weakly, or a sequence of bounded linear functionals that converges weak starly, then that sequence is always bounded. So it's only natural to ask whether now here in this setting for bounded linear transformations you have a similar statement, and the answer is positive, and this is contained here in this theorem. So if you have, however, not just arbitrary normed linear spaces, you need Banach spaces. That is because, again, if you think back how these other two theorems were proven about boundedness, there you use the principle of uniform boundedness, you need completeness. That's why this is natural to have it here as well. And the statement is as follows: if you have a weakly convergent sequence, then, well, that sequence is bounded in the operator norm, right? And that in particular means if you have it already for the weakly convergent sequences, then of course you have it in particular also for the uniformly and strongly convergent sequences, right? Because again of this tower that goes downwards. All right, so let's prove this now. Again, this will be an application of principle of uniform boundedness. So if for all points x in the domain space and all bounded linear functionals on the target space, we have the weak convergence. So remember, by definition, this means f of t and x going to f of t of x as n tends to infinity. Then, what does this tell me? Well, just remember how weak convergence was defined. Then the sequence Tn of x n1 to infinity converges weakly to t of x, right? So remember, we wrote this in symbols as Tn of x with this sort of half arrow to t of x as n tends to infinity. Yeah, but then we know, so by that previous theorem about weakly convergent sequences being bounded, we know there exists, so there exists constant c, cx positive, so that Tn of x less than or equal to c for all indices small n, right? Hence, for every point in the domain space capital X, supremum of these guys here, Tnx. And by the way, here we could of course index the norm, because I wrote in the statement of the theorem that there's two norms, one on X space, one on Y space. So here these are elements in the Y space, so let's put the index in there. That this thing here is bounded, and that means, which says the family F, which is Tn and 1 to infinity, that's a family of bounded linear transformations, is pointwise bounded, right? And now you see clearly you need that X and Y are Banach spaces. Thus, by pub, we have that the supremum of all these guys, this family pub, asserts that that family is uniformly bounded. Alright? And so Tn an operator norm less than or equal to c for all n in n. Alright? And that finishes the proof of the theorem. Okay, good, excellent. So that was a very short section here up front in chapter 4. Just three more convergence types that will play a role in the things to come. And now, more importantly, the next section about adjoints. So remember when we were doing in chapter 3 the section on duals and double duals, the first thing we did there was defining the so-called dual transformation, right? So if you have, let's light it here in yellow. So if you have bounded linear transformation between two normed linear spaces x and y, then you can cook up a object which is the dual transformation with the t that goes, well, the other way, but from the dual spaces to the other dual space, right? Like this. And that dual transformation has some very nice properties. It's in particular mighty useful if you want to figure out whether certain spaces are reflexive, right? Because you only have to apply this t with the little t on top sufficiently often, and then you will be landing in the bidual of your given space. And I said, so we will call this stuff there in yellow the dual transformation, but there's other names around in the literature. Some people already call it adjoint, in particular Banach space adjoint, if those spaces x and y are complete normed linear spaces. And I said back then in the video, this is because, and I think it's also written in the notes, this is because the dual transformation shares certain properties with another bounded linear transformation. That's the adjoint that we will define in a few seconds. And that's why people tend to call both of these guys adjoints, right? But I don't do that, because although the upcoming adjoint there in this section is somewhat similar to the what we call dual transformation, this is only a similarity on the surface. If you look deeper, they are very different objects from one another, so I prefer to use different names for different things. That's why. All right. So now let's get started here. So the adjoints, this will be the Hilbert space adjoint, opposed to what some people call that yellow stuff, Banach space adjoint. It is defined here in this first result. So if you have two Hilbert spaces, H1 and H2, and they come both with their own inner product. So you see here that I index the inner products now with the indices 1 and 2, right? And now if you have a bounded linear transformation, capital T, then for that guy there exists a unique transformation T star, right? So unlike putting up here this T for the dual transformation, for the adjoint, the Hilbert space adjoint, I will always use the star, right? So that is a bounded linear transformation that again goes the other way. It doesn't go from space 1 to space 2, but rather from space 2 to space 1, but no dual spaces up here, right? There's no H2 star as it was here sort of up in this world, right? Of course, you know, since these are Hilbert spaces, remember Hilbert spaces are always isomorphic to their dual spaces, so you know, maybe that's the reason why there's no star, but okay, let's keep going for the moment. So what is the defining property of this unique transformation that we will call the adjoint? It will always be clear that we are dealing here with Hilbert spaces. We are only defining this adjoint here in a Hilbert space, so we can drop the word Hilbert space adjoint, just call it adjoint. And the defining property here is this one. So you have these two inner products, remember. Here's the one from the second space, here's the one from the first space. And what it says is for any points or vectors x in the first Hilbert space, y in the second Hilbert space, you can look at the inner product tx with y. So tx maps to y, to the H2 space. So these are indeed, you take the inner product of two objects in the second Hilbert space. So that's why the left-hand side makes sense. And likewise, you can think about the right-hand side. It also makes sense because T star takes input from the second space. It spits out something in the first space. And then you take the inner product with something in the first space, right? So also the right-hand side is well defined, well, provided this adjoint exists, but we will clarify this in a moment. And now the crucial property is these two things have to be the same, right? That is the property that uniquely defines the so-called adjoint, all right? Good. If you think back to linear algebra, that is maybe something that you have encountered in inner product spaces. Matrices that do this are usually called Hermitian matrices. So those matrices, those are square matrices, such that that matrix is equal to the matrix that you get when you swap rows and columns and you put complex conjugate bars on all the entries. Precisely this yellow box generalizes this to infinite dimensional Hilbert spaces, and the associated operator is called the adjoint. All right, good. So enough said. Now we have to prove this stuff. So first of all, I already said this in words. Start by recalling that each H sub I here is isomorphic to its own dual space. This is a consequence of Riesz representation theorem. We did it in detail. All right. So now let C sub I denote that map that sends a vector to that linear functional. Denote the map that assigns to each y in the ith Hilbert space the bounded linear functional, and I've used this notation before, so I make a dot in the first entry and then I. So this is a linear functional because the input vector x that you would stick into the first vector where that little dot appears, right? So now Riesz representation theorem tells us precisely the properties of this map C sub I, right? So note that, actually it's recall that, note that Ci is a conjugate linear. So linear is clear what this means. Conjugate linear means that if you look at linear combinations, the scalars, they in general get complex conjugate bars on tops, and that's simply because the y here appears in the second entry. Remember when we proved that Hilbert spaces are isomorphic to their dual spaces, the map that I set up had here a bar on top, and I said that bar you need because you want a linear isomorphism. Here, for the purposes of this proof, it's irrelevant whether that thing is linear or whether it is conjugate linear. So I'm just being lazy here and I'm not dragging the bar around it, but then I have to write here conjugate linear. Okay. What else? Is this an isometry? This is simply because in Riesz representation, maybe I write it here, there was this inequality between the linear functional f that you start with, so this on the left is the operator norm, and then there's this unique element y sub f, so that the linear functional is inner product with y of f, and these two norms are the same, and that's precisely what's written here, that this map is an isometry. Okay. Good, and what else? Well, it is bijective, right? So for each linear functional there is a unique y sub f, such that you can represent the functional in the fashion written there. Okay, so this is all, this line here is all written down in the Riesz representation theorem, which was proven in chapter 2. All right, so having this now define the map. So we will construct it from scratch, that adjoint h2 to h1 by, well, T star is what? So it's a bijection, so I have the inverse here, and then I hit it with the dual transformation of T, and then up front with the map that is C2, all right? Using the dual T, well, with the T which goes from the dual space of H2 to the dual space of H1. Okay, now what we will do is we will check that this guy satisfies that yellow box. Note that T star satisfies, and then we will have to prove, well, that it's bounded linear, and then it's sort of uniquely determined by the yellow box. All right, so let's start, say, from the left. So txy, comma 2. Now remember the map C sub I. So C sub I sends a vector to that inner product with y in the second entry. So here, that's precisely what happens, right? You got y in the second entry, and it is in the second space. So this would be C2y, right? This is by definition a linear functional. And then what I do is here I evaluate that linear functional on this green vector, right? So this would be evaluated at t of x, all right? Now comes the usual trickery. You gotta remember how the dual transformation is defined. This is t with the little t, c2y of x. This is definition of the dual transformation. You can look it up in the chapter on duals and biduals. And now, of course, now you just trick around a little bit. You want to generate this guy after all, so you write a c1 on the left, and then you would have here c1 minus 1 tt c2y x, and then of course here you recognize this is precisely the adjoint, so you have c1 adjoint of t y x, and now all that you have to do is you have to remember what does c1 do. So c1 sends it to a inner product in the first space. Let's have some more space here. And this one here, that's the vector that appears in the second entry, so t star y. And that vector here, the x, that's the one that you evaluate the linear functional on. So that stands there, okay? And if you now look, this here equal to that is precisely the property that I wrote in the yellow box, okay? So we have it. That thing satisfies what we want for all x in H1 and y in H2. Okay, excellent. Now we have to figure out the linearity on the boundedness, but that is clear. So I will just say clearly T is linear because it's a composition of linear maps. C2, C1, the inverse thereof, and the dual transformation are all linear maps. So the composition is linear, that's clear. And what about boundedness? Well, all three of them are bounded linear transformations, so the composition will also be bounded linear transformation. In fact, you can give an upper bound for the operator norm, just using the submultiplicativity of the operator norms. You have this one, and this is finite because all three norms there are finite, right? Good. Now, so that is clear. So we have bounded linear, the adjoint is bounded linear transformation, and now we have to figure out that, well, there's only one who does what we want it to do. So finally, if there are, or if there were, I should say, if there were two guys, say T1 star, T2 star, from LH2 to H1, such that, well, X T1 star Y, 1 is txy2, and at the same time x t2 star y, 1 for all x in H1 and y in H2. Then insert, since this is valid for all vectors x, so just take x equal to the difference t1 star y minus t2 star y, and conclude. So what you do is in this equation up here, you look at this green shaded thing, green underlined thing, and this one, you bring them both to one side, and then you would have inner product x with the difference t1 star y minus t2 star y is equal to 0. That has to be valid for all x and for all y, so then you just substitute x as written in there, and then you get the norm squared of t1 star y minus t2 star y, which has to be 0, and that has to be valid for all y. Then you take again the optimization over y, you generate the operator norm of the difference t1 star minus t2 star. That operator norm has to be equal to 0, and then you get that t1 star is equal to t2 star, right? And conclude, oh, it's not in green, in blue, and conclude t1 star equals to t2 star, right? So this argument we have applied several times. All right, good, nice. So now we have the Hilbert space adjoint, or simply adjoint. Now we will summarize its key properties, and from those key properties you will clearly see that, well, some of them are actually identical in a sense to what the dual transformation does, but others are very different, right? So let's list them here. So 2 are already written here. So statement is as follows. So if you have two bounded linear transformations, T and S. So T goes from space 1 to space 2, and S goes from space 2 to space 3. Both bounded linear, and those 3 spaces are all Hilbert spaces with their own inner products. All right, then you let T star and S star denote the corresponding adjoints. Then here's a bunch of properties. There will be 6 properties. Okay, so first one, the mapping that assigns to each bounded linear transformation its adjoint is a conjugate linear isometric isomorphism. Okay, so linear, okay, that's clear what it means. And conjugate linear, that I explained earlier, it just means when you have the scalars in front, and if you decompose, they come with complex conjugate bars, right? That's by conjugate linear. That's already the first difference from the dual transformation, because the dual transformation was in the dual transformation, when you had this statement sending T to its dual transformation, that was a linear map, right? Here it's already conjugate, only conjugate linear. Okay, then next, the isometry. That's also what this guy does up here. This is also an isometry, because you have T in norm is equal to the norm of the dual transformation. You have the same here, but now this property that this is an isomorphism is not something that you have up here at all. Okay, that's not true at all, right? So that's the first big difference. Now, second property, that's very much what you have for the dual transformation. So if you look at this composition here, S and T, and you compute the adjoint thereof, then you can just compute the individual adjoints and then compose them in the reversed order. The dual transformation satisfies formally the same thing. Okay, formally the same thing. All right, now third property, if T is invertible, then so is the adjoint, and, well, there's the formula, the adjoint of the inverse is the inverse of the adjoint, right? So that property also formally is something which the dual transformation has, okay? But however, now what comes now afterwards, this is something which the dual transformation does not have. And I mentioned this back in the day when we listed the properties of the dual transformation. So if you take the adjoint and compute its adjoint, then you go back to the original map T, okay? But I said back in the day, if you do this for the dual transformation, then you don't get back. And this should be clear why, because this here is a bounded linear transformation from X to Y, whereas this here is bounded linear transformation from the biduals. And they in general are not the same as X and Y, right? Even if you are in reflexive Banach spaces, then they're only the same up to isomorphism, right? So that doesn't work at all in the dual transformation world. But here for the adjoint it does, right? 5. Well, let me move this stuff here out of the way. 5. The map T star is continuous. Okay. Let's move this here and sort of make the element here. Is continuous in the weak and uniform operator topologies. Now that's fancy language for a very simple property. I will explain once we prove it, but not in general in the strong operator topology. Well, what it really means is that if you have a sequence of operators that converges weakly and uniformly, then the corresponding sequence of adjoints also converges weakly and uniformly. That's what it means. That's my continuity. But this is not true for the strong operator convergence in general. For the strong convergence in the strong operator topology. Okay, and then the last property, and we will prove this in the next video, is that's actually very useful. So if you look at a joint and T itself composed in this way and in the other way, in general these are not the same, but if you throw the operator norm around both things, then in operator norm they are the same, and even better, that is the same as the operator norm of T itself squared. Okay, so these are the central properties of the adjoint that we will prove in the next video. We will then have examples and then build up more theory. Okay, I'll see you soon.